Could the universe accidentally become conscious? Imagine the universe in an age so distant that almost every familiar source of light has disappeared. The stars have exhausted their fuel, galaxies have faded or moved beyond one another's reach. Planets no longer orbit warm suns, and the conditions that once allowed life to develop have become rare or vanished entirely. By then, space would be dark and thinly populated, with change occurring on timescales far beyond ordinary understanding. Somewhere within that apparent stillness, however, matter might briefly settle into an unusual arrangement capable of supporting awareness. The observer would not need to resemble a human brain. It could be a temporary pattern in particles or fields, carrying what seemed to be memories of a body, a family, and a life beneath a blue sky. None of those events would need to have happened. The memories could exist only as part of the arrangement itself. A moment later, the pattern would break apart, the thought would end, and the universe would return to silence. This hypothetical observer is known as a Boltzmann brain. The name can be misleading. It encourages us to picture a recognizable brain floating through space, complete with eyes and an expression of alarm. That is not essential to the idea. A Boltzmann brain can mean any observer that arises through an extraordinarily unlikely fluctuation, rather than through the long history of stars, planets, chemistry, and evolution. No such observer has ever been detected. The idea appears instead as a consequence of certain theories about cosmology, entropy, and probability. To understand why, begin with statistical physics. Imagine opening a bottle of perfume in one corner of a room. At first, the molecules are concentrated near the bottle. As they move and collide with the surrounding air, they spread throughout the available space. Nothing in the basic laws of motion strictly prevents those molecules from gathering together again. Every molecule could, in principle, happen to move back towards the bottle at the same time. We do not expect to see this because the number of scattered arrangements is overwhelmingly greater than the number of concentrated ones. There are countless ways for perfume molecules to be spread around a room, but relatively few ways for all of them to occupy one small region. This imbalance is related to entropy. Entropy is often described as disorder, although that can be an imperfect description. More precisely, it concerns how many microscopic arrangements can produce the same larger condition. A room with evenly dispersed perfume can be realized in vastly more ways than a room in which every molecule happens to sit beside the open bottle. That is why systems tend to move towards higher entropy states. They are not being forced to become messier. They are moving from rare arrangements towards arrangements that are statistically much more common. With large numbers of particles, this tendency is extraordinarily reliable. It is not necessarily absolute. Small fluctuations occur constantly. A few molecules may briefly gather in one area before spreading again. Larger fluctuations remain possible in principle, but they become rapidly less likely as the required organization increases. The chance of all the air in a room collecting in one corner is so remote that nobody seriously expects to witness it. Cosmology, however, introduces timescales that ordinary intuition was never built to handle. Suppose a universe survives for an indefinitely long period in a condition where fluctuations remain possible. Even an event with a fantastically small probability may eventually become relevant. Given enough time, a temporary arrangement of matter might form a simple machine. Over a far longer interval, a fluctuation might produce a functioning observer. The waiting time could be so immense that writing it down would require an absurd number of digits. But if the available time has no meaningful limit, rarity alone may not remove the possibility. This line of reasoning developed from the work of the 19th century physicist Ludwig Boltzmann. Boltzmann helped explain entropy statistically. He showed how the familiar direction of thermodynamic change could emerge from the movements of enormous numbers of particles. His work also led to a cosmological problem. Why did the universe begin in such an ordered, low-entropy condition? The early universe was hot and dense, but in the gravitational sense it was remarkably smooth. Matter had not yet collapsed into the complex structures, black holes and uneven distributions seen later. That low-entropy beginning allowed stars to form, planets to develop, and life to evolve. It created the physical difference between past and future on which complex processes depend. One early suggestion was that our observable universe might itself be a rare fluctuation from a much larger equilibrium state. Most of reality could remain in thermal balance, while an exceptionally unusual region temporarily dropped into a lower entropy condition. That region could then develop into the organized universe we see. At first, this seems to offer an explanation. We observe an ordered universe because observers can only develop in places where enough order exists to support them. The difficulty appears when we compare the size of the required fluctuations. Producing an entire observable universe would be far less probable than producing only the minimum arrangement needed for an observer. Nature would not need to recreate billions of galaxies, a real planet, a genuine history, and a long process of biological evolution. It would only need to produce a mind that believed those things existed. A temporary observer with false memories requires a smaller departure from equilibrium than a whole low-entropy cosmos containing authentic records of the past. That is what turns the Boltzmann brain from a strange image into a serious problem of explanation. Consider two observers. The first develops through an ordinary cosmic history. A universe expands from a low-entropy beginning. Stars form and produce heavy elements. Planets emerge around later generations of stars. Chemistry becomes biology, and evolution eventually produces a conscious being. The second observer appears through a random fluctuation. Its structure happens to include similar memories and beliefs, but there was no childhood, no planet, and no history behind them. From the inside, the two observers might be indistinguishable. Each remembers waking that morning. Each believes it has lived for years. Each looks at its surroundings and forms conclusions about reality. The first belongs to a history that genuinely produced it. The second appears already carrying what feels like the memory of such a history. Now, suppose a cosmological theory predicts a finite number of ordinary observers, but an unlimited future in which random observers continue to appear. However slowly they form, their numbers could eventually become enormous. In some models, they might vastly outnumber observers who arose through normal cosmic evolution. The statistical consequence is troubling. If you regard yourself as a typical observer within such a theory, you should expect to be one of the accidental ones. You should expect your apparent memories to be false, your surroundings to be temporary, and the universe beyond your immediate awareness to bear little resemblance to what you believe. This does not prove that you are a Boltzmann brain. The stable and consistent world we observe is one of the main reasons physicists distrust models dominated by them. Your surroundings do not dissolve from one moment to the next. Other people report compatible experiences. Experiments can be repeated. Records agree with one another, and observations reveal a universe with a coherent history stretching back billions of years. A randomly assembled observer could briefly experience the illusion of all this consistency. Most accidental observers, however, would not be expected to find themselves in such an orderly environment. They would be more likely to appear amid confusion, with perceptions and memories that did not fit what surrounded them. The fact that we observe a structured universe therefore counts against theories predicting that most observers should be isolated fluctuations. The argument also threatens the reasoning used to support it. Suppose you use evidence, memory, and logic to conclude that a theory dominated by Boltzmann brains is correct. According to that same theory, you're probably an accidental observer. Your evidence was probably never gathered. Your memories are probably fabricated, and the reasoning process you trust may be only a temporary arrangement of matter. The theory undermines the grounds on which you came to believe it. Physicist Sean Carroll describes this as cognitive instability. A theory of this kind may be mathematically expressible, but it cannot easily be both true and rationally believed by observers within it. For cosmologists, this makes Boltzmann brains useful as a test of a model rather than merely a curiosity. When a cosmological theory predicts overwhelmingly more disordered observers than ordinary ones, researchers treat that as a warning. The problem may lie in the model itself, in the way probabilities are being calculated, or in the assumptions being made about the distant future. One possible escape is for the universe's current vacuum state not to last forever. In physics, a vacuum does not always mean complete emptiness. It can mean the lowest energy state available under particular conditions. Our universe may occupy a vacuum that is stable, or it may be metastable. If it eventually decays into another state before Boltzmann brains can accumulate in overwhelming numbers, the paradox may be avoided. Some calculations compare the rate at which hypothetical Boltzmann brains would appear with the rate at which different vacuum states decay. The details depend on the cosmological model and on difficult questions about how probabilities should be assigned in an eternally expanding universe. There's also disagreement about whether the proposed fluctuations correspond to real events. Quantum theory can assign a non-zero mathematical weight to arrangements resembling observers within a vacuum state, but that does not necessarily mean functioning observers physically appear, think, and disappear. Some researchers argue that a truly stationary quantum vacuum does not contain the changing, out-of-equilibrium processes required for consciousness. From that perspective, the mathematical possibility of an observer-like configuration should not be confused with an observer actually coming into existence. Other approaches to quantum mechanics and cosmology reach different conclusions. The result is not a settled prediction, it is a dispute at the edge of our understanding. Much of the argument rests on questions that remain unresolved. We do not know the final state of the universe, how long its present vacuum will survive, or exactly which physical processes are sufficient for consciousness. A complete theory linking gravity and quantum mechanics may change the problem again. These uncertainties matter. A temporary network spread across dust, fields, or celestial objects might sound capable of awareness when described in broad terms, but complexity alone does not guarantee consciousness. The arrangement would need to perform whatever physical processes experience depends upon, and science has not yet identified the full requirements. The Boltzmann brain remains hypothetical from beginning to end. Its real value lies in what it exposes about evidence. Memories matter because they appear within a wider network of consistent records, repeated observations, and shared experience. A cosmological theory must therefore do more than describe what is mathematically possible. It should also explain why observers encounter the kind of stable universe we do. The most difficult question is whether a theory can be rationally accepted when it predicts that most observers who believe it are mistaken about their own history. The paradox forces cosmology to account not only for matter and energy, but also for the observers using those theories. We normally picture ourselves as spectators looking out at the universe. The Boltzmann brain problem reminds us that we are physical events within it. Any complete cosmological theory must explain why observers like us arise, why our memories appear connected to a real history, and why the world remains stable long enough to be investigated. It may be that the universe will never produce an accidental observer. The physical processes required could be impossible in its final state. But if such an observer ever appeared, its existence might last only an instant. The memories contained within that instant could still seem to describe an entire life. From its own point of view, there would be no distinction between a history that genuinely happened and one that existed only as part of its temporary physical structure. That brief experience would be all the reality it had.